Salvador Cordova for coming to talk to us. He is going to tell us about gamblers' epistemology as an alternative to impractical naturalism. So he has a lot of experience in the gambling industry. He might tell us about that. So this promises to be a great talk. All right, Salvador, it's all yours.
Well, just a little bit about me, since some may be joining. It's not quite 12:15. I saw on the schedule that I was scheduled for 45 minutes. So I divided my talk into two parts. So I'll have the main part that's about half an hour, and I can fill out the rest of the 15 minutes. I was in a documentary about Christian gamblers who won $3.5 million from casinos. So that's a little bit of my experience in the gambling industry. All right, so thank you all for tuning in to my presentation, Gamblers' Epistemology as an Alternative to Impractical Naturalism, the Unwitting $500 million Wager Against Evolutionary Theory by the NIH. As I mentioned, this will be in two parts. Fasten your seatbelts. I like to communicate visually. There are about 65 slides. The main theme of the presentation is best illustrated by a simple historical example. And that example is of the atheist Haeckel versus Pasteur. In 1876, Haeckel said, if we do not accept the hypothesis of spontaneous generation, then at this one time in the history of evolution, we must have recourse to the miracle of a supernatural creation. It's amazing that he said this in 1876 because 15 years earlier, Louis Pasteur was awarded the prize by the French Academy of Science for experiments disproving the spontaneous generation and establishing the law of biogenesis. This supported the germ theory of disease and made substantial advancements to medical science. There's a lasting tribute to Pasteur on practically every carton of milk. It shows how the scientific method prevailed over the impractical naturalism of Haeckel. So lessons from Haeckel versus Pasteur. One thing that we learned is the operation of the natural world in the present cannot be extrapolated absolutely for all time. My personal opinion is naturalism should not be conflated or equated with empiricism or science. If naturalism rules out exceptional events, it is actually in conflict with physical evidence. And also, on what basis can any philosophy or methodology possibly rule out exceptional events? So as an alternative to what I call impractical naturalism, I suggest gamblers' epistemology. Gambling does have a very bad reputation, but there have been some successful gamblers, such as Edward Oakley Thorpe. He was the hero of the true story that was written about in the book Fortune's Formula. He's an MIT math professor, and he turned into a casino shark, used gambling math there, was successful in that arena, and then he applied gambling math to investment and became a billionaire. One of his pupils, Bill Gross, by the way, manages a $1 trillion hedge fund. So the science of gambling, I think, does have something to say about the operation of the real world. Those are Thorpe's books, The Mathematics of Gambling and Beat the Market, where he wrote some time ago, and he actually outlined his techniques even before he started his $1 billion hedge fund. So I'm not really going to define gamblers' epistemology. It's a little bit amorphous. It's really more of a collection of principles. Probably the most important principle for the sake of this discussion is what I call the paradox of definite practical knowledge in the face of maximum uncertainty. That is to say, we can actually be fairly sure about something even though we're faced with a lot of uncertainty. The best example I have of that is if we have 500 fair coins in a jar and we shake the jar vigorously and pour it out on the table. This process maximizes the heads, tails uncertainty of each coin. But we actually have definite practical knowledge that the coins through this process will not come out 100% heads. So that's an interesting paradox. The mathematical expectation is that we'll have about 50% heads, not 100% heads. This is based on the law of large numbers. And by the way, an evolutionary biologist by the name of Nick Matsky, who is very prominent in the infamous Dover versus Kitzmiller versus Dover trial on intelligent design, when I posed the question to him, if you were to happen upon a table that had all the coins, fair coins, and they were in the 100% heads configuration, would he rule out chance? And he had actually a hard time. He refused to answer the question, which I found surprising in some respects, but not in others, because I think he knew where I was headed with that. Incidentally, the heads coins issue relates to the problem of chemical homochirality in the origin of life, and it is an evidence against spontaneous generation. So it's not practically possible to get 100% heads out of fair coins if you have a large number of coins through an uncertainty maximizing process like shaking a jar of coins. It could be applied to other sets of objects like dominoes or cards. An uncertainty maximizing process might be, say, a tornado. A tornado will not result in these configurations as you see pictured here. I would call these configurations exceptional. They are not typical. To actually demonstrate they're exceptional, it takes a little bit more rigor, but it can be done. It takes more rigor than what I did with the coins, but it can be done. Exceptional configurations, I'll say, can be said to possess high specificity. And here are just some more examples of exceptional configurations, like the lock and key configuration in the man-made world, or the lock and key configuration of molecules in the biological world. Framing the spontaneous generation question in terms of naturalism versus supernaturalism, I actually think is a little bit counterproductive. It muddles the more basic scientific question. The basic scientific question is whether life is a typical or exceptional chemical configuration. So here we have physical configurations of objects that are someone has their microphone on. Anyway, we could see these objects have an exceptional configuration, and we could actually make the same analyses and conclude that chemicals are either an exceptional configuration or a typical one. Life is an exceptional configuration, astronomically so. Now, some people have said that, well, they're infinite. Some people have said there are an infinite number of ways to make lock and key, infinite number of ways to make chemical replicators, and therefore life is not that special. Well, I would counter that objection by saying there are an infinite number of ways to make lock and key systems like this, but it doesn't make a lock and key system highly probable. So one thing I'll point out about impractical naturalism, it rules out exceptional phenomenon as a matter of principle. So there's some principles of Gambler's epistemology. I'm not going to define what that epistemology is, and I'll explain why. One of the principles is uncertainty about what is true is the norm. Decisions are made often with incomplete knowledge, but there's still a way to define expected versus exceptional events despite maximum uncertainty. There's also an old proverb, play the hand you're dealt. And as far as making money, as Ed Thorpe did, you apply Pascal's wagering methods where there's cost-benefit or risk-reward. The reason I'm not formalizing the epistemology is there's really no point in formalizing an epistemology where uncertainty is a basic axiom. But despite all this, profit is still possible despite uncertainties if we apply gambling principles. There are other examples of impractical naturalism, not than just Haeckel and Pasteur. Some notable ones: the idea of an eternal universe versus a non-eternal universe. The naturalists preferred the eternal universe because the non-eternal universe indicated something special. The same thing, the conflict between insignificance of Earth versus a privileged planet. The scientific evidence continues to pile up that we live on a privileged planet. and we live in a fine-tuned universe. And this is somewhat uncomfortable for naturalism because privileged positions, privileged planet, anything exceptional just begins to get a little bit too close to the miraculous. And really one area that I'm very interested in is the impractical naturalism of evolutionary biology versus what's happening at the National Institutes of Health ENCODE project. So speaking of ENCODE, let me talk about ENCODE. There's a $793 million wager on the ENCODE project and its sister project. Really, actually, that number fluctuates a bit. There has been about $500 million committed or spent. In 2003, we had the ENCODE project that was launched. It had a budget of $288 million. It was highly successful. It had 2 follow-on projects, the Roadmap Epigenomics project, which is budgeted at $300 million, and the E4 project, which is yet to come online. But this is a lot of money being wagered on an idea. So to get an idea of what the ENCODE project is, I'm sorry, I'm going to have to get into some technical stuff, and I know there are a few biologists out there, and for those that aren't, please bear with me. This will sort of give force to my argument. The major concept is that DNA is the same in each cell of an individual, but it is used differently in each cell. DNA is a multi-purpose molecule, and some people call it multifunctional, and it is polyfunctional. This is especially true in multicellular creatures, and more so in multicellular creatures than in bacteria. Here's a diagram. We have mostly the same DNA in each cell. There are 210 to 300 different cell types and over 100 trillion cells, and they're all slightly different and in various developmental stages from conception to adulthood. DNA is used slightly different in each cell. So that's really the point. So ENCODE's role then is to figure out how this is done. And so this is a diagram, and we have here this line here represents conceptually a gene, and the ENCODE consortium will conduct all these experiments listed in the gray boxes, and they'll do this for every cell. They'll do this for every stretch of DNA in a cell, and they'll do these sets of experiments for various cells. The ENCODE project surveyed 150 cells, and the follow-on Roadmap Epigenomics surveyed 111 cells. But this is really just the tip of the iceberg. This is just scratching the surface. There are a trillion cells in the adult human in various developmental and stages or cell phases. So we're not even beginning the exploration, even with the nearly almost, we're looking at maybe $1 billion investment. We've only scratched the surface. So to maybe explain a little more detail about what they look into, a little bit by way of analogy, this picture here is a picture of man-made random access memory. It's an old-style random access memory, and the salient features are you have these little cake-shaped memory elements, and they are connected by wires like that. So that's man-made random access memory. The next slide, I have what I call God-made or nature-made random access memory. I prefer God-made. It too also has these cake-shaped memory elements called nucleosomes, and the wires connecting them are the DNA. I'll give you another graphic here. On the left, this is the conceptual diagram, but up here on the upper left corner is an actual microscopy picture of these beads on a string, and you have the little memory elements like that connected by the wire of DNA, and it looks hauntingly similar to the man-made random access memory. So on the left is what I call God-made, and on the right, man-made. Now I'm just going to zoom in. Down here, this diagram. I'm going to zoom in so you could get a little bit better picture of what's going on. So we have this little God-made memory unit, and I'm going to zoom in even further down here. And you could see it. Okay, this is a nucleosome. The little the things that are marked H3, H2A, H4, H2B, those are called histones. They are proteins. And on these proteins, we have these amino acid residues. And in the diagram, it's numbered from 1 through 79. Not all of them are listed. And in each of these amino acid residues, they can be chemically modified. Hence, they could store at least 1 bit of information, sometimes often more, because there's a whole suite of chemical modifications that can be affixed to this. And there are, to do all these wonderful things, there are read and write heads. In the literature they call them readers, writers, and erasers, and they can modify little elements. A single amino acid residue can store those bits. And I'd like to focus specifically on this amino acid residue on histone 3, lysine number 27. I'm going to show you the machinery that flicks that bit. It's really amazing. This here is a picture of a polycomb repulsive complex, and I'm just going to highlight it here. These wires here are the DNA wrapping around the histones, and those are the those are the memory units here. And this tail that is described here that has lysine 27, if you can imagine, it's this tail here that inserts into this red little machine marked EZH12. And what happens is the tail goes in there and it gets set. It gets a methylation mark put on, and that's how the bit is flipped on. So all this, what I'm describing is the random access memory inside the cell. So the DNA is a read-only memory, but some of its modifications and associated machinery around it is random access memory. And we call this random access memory the epigenome. And the epigenome is a serious science projected, according to this diagram, to have an $8 billion therapeutic market. And the ENCODE project is providing a lot of data that helps this market, helps researchers in that market. So as the researchers did more and more of this, they began to be very impressed with what's happening inside the cell. So they said they realized DNA is multi-purpose, less likely to be highly functional. The ENCODE researchers claims that DNA is highly functional, and these claims contradicted the claims by evolutionary biologists that most DNA is junk. So this did not sit well in some quarters. All of this really is just a consequence of ENCODE's research into the DNA ROM and RAM. And by the way, the system can be likened to a Turing complete computer. So this headline in 2012, 9 years after the initiation of ENCODE, in the prestigious journal Science, ENCODE project writes eulogy for junk DNA. This week, 30 research papers, including 6 in Nature, and additional papers published online by Science sound the death knell for the idea that our DNA is mostly littered with useless bases. This did not sit well with certain evolutionary biologists, like this one pictured here, Dan Grauer, professor, University of Houston, who said at the 2013 meeting, Society of Molecular Biology and Evolution, if ENCODE is right, evolution is wrong. And that's not all he had to say. On his website, he said, the evolution-free philosophy of ENCODE has not started in 2012. The wannabe ignoramuses, self-promoting bureaucrats, and old-fashioned crooks of ENCODE are protected from criticism and penalties for cheating by the person who gives them the money. Thus, they can continue to take as much money from the public as their pockets would hold, and in return, they will continue to produce large piles of excrement that are hungrily consumed by gullible journalists who double as science editors. And on his website, just to let you know how he feels, this is on an official university website. He shows a picture of his granddaughter giving ENCODE the middle finger. So I would say, even though I'm sympathetic to ENCODE, I'd say it's still a tad premature for either side to declare victory. in the junk DNA question. Money has to be invested to resolve the question. I'd say the advantage goes to ENCODE. Grauer does have a point with the C-value paradox for those biologists out there. I can't get into it, but he does have some merit in what he's arguing. It will take centuries of expensive laboratory work to really settle this question definitively. Could be in the trillions of dollars. Going on, we still have questions on how to spend money, but unless we know in advance what is and is not functional in DNA, we have to search on the assumption that DNA could be functional. So there's no harm in assuming most of the genome is functional, but this really does not sit well with Grauer. But one thing I've noticed, he's never specified what experiments should not be funded by ENCODE, and I showed earlier the list of experiments. Sorry, here he's not highlighted which of these experiments should not be done, and on which cells we should not study. So, in my humble opinion, he's really behaving just like a sore loser. He's not really making much of a scientific argument. He's just making a lot of noise. If we apply Pascal's mathematics of wagering, don't waste money on prospects with zero payoff. Place money where there's a probability of being right and a potential payoff for being right. I point out if Grauer is right, there's zero payoff. However, if ENCODE is right and we don't take the bet, there's a lot to lose because of willful ignorance of medically significant facts. So conclusion, ENCODE research is already leading to treatments of diseases. In contrast, $177 million is wasted by the National Science Foundation on untestable evolutionary phylogenies, evolutionary trees with no practical utility. So I argue bet on ENCODE, don't bet on the impractical naturalism of Dan Grauer and friends. I'd like to pause a little bit for some questions or comments before going to part 2.
All right, since we have a lot of people in this conference, I will look for people sending me requests and then I'll unmute them so they can talk. Yeah, or go ahead and type me your question into the chat. Okay, Jim LeMaster has a question. All right, Jim, you're up. If you're talking, you may be muted because I can't hear you.
Eric, can you hear me?
I can hear you. You need to move out presentation. Okay, yeah, I'm just going to unmute everyone. Okay, so everyone is unmuted now.
So Jim, the mute button, if it should be at the top of your screen, there's a little microphone. But Sal, I was going to say, I don't think the C-value paradox is really that much of a paradox. I think it's from an old view of genetics.
Well, actually, that would be good news to me. Maybe I gave Dan Grauer too much credit. One thing that we are finding is the epigenome is actually implemented differently in each cell. And I think it could be really exciting that just how much technology is in each cell. It's different. We're finding it's different in every cell. But thanks for the good news. I hope that's the case.
Can you hear me, Sal?
Yes.
Okay. All I wanted real quick was I really am fascinated by that slide you had where you're visually setting side by side the two kinds of RAM, the RAM that's in our cells versus the RAM that's in the old computer. Is that possible for you to send me that, and can I use those slides without violating anybody's copyrights?
I actually don't know about the copyrights, but you can. I think some of them cannot, by law, have copyright because they were developed with government funds. The one for the random access memory for the man-made. By the way, it looks like my screen share is paused. Could I show that diagram again?
Yeah, here, I'll give it back to you. We also got a question from Heather Zeiger.
Yes, Heather.
Hey Sal, thanks for the presentation. I had a question. Hasn't there been some findings in cancer research that epigenetic factors may be what are causing the cancer cells?
Oh,
I'm thinking of leukemia research.
Oh, absolutely. Absolutely. I'm getting some feedback.
Yeah, I'm gonna mute everyone real quick so that you can talk. All right, go for it.
Actually, what's driving this almost $700 billion of research is cancer and heritable diseases. And we're finding a lot of the cancers are in the random access memory. So it's rather amazing that we find some cells that are cancerous that the DNA doesn't look that bad. And they're trying to figure out what's going on. They realize that there are all these epigenetic changes in this random access memory here with the bits being flipped on and off. And that was associated with cancers that are acquired. Now there is definitely a heritable component, but now we're seeing this epigenetic component, and that's where the therapeutic market is we're finding there are a lot of environmental factors like the things we eat or the chemicals we're exposed to that start to flip these bits on and off inside the cell. And so some of the therapeutic targets are trying to get these bits flipped in the right way, and they're trying to basically reboot some of the RAM. So yes, that's a very good question. Incidentally, I'm down at the NIH almost every week now, just talking to the researchers, and they're the ones who actually provided some of this information.
Okay, we have another question from Gary Gallon. I'll just read it out for you. He says, I was fascinated by the part about RAM memory. Is there more information online showing what you have for network interconnections, including how RAM is being addressed?
The field is, short answer is not really, and we actually don't know how the memory is actually addressed. We think the DNA has something to do with it, but it looks like it's vastly complicated. So maybe in the interest of time, how about I try to move on to the second part, because that'll actually answer some of Gary's questions. Would that be all right with everyone?
Yeah, let's go ahead and do that.
Okay. Part two, I'd be remiss if I didn't acknowledge the guy who really made this presentation possible, John Sanford. For those who don't know him, he's the inventor of the gene gun. His invention right there is at the Smithsonian National Museum of American History. A large fraction of genetically modified organisms are the result of his gene gun, so I have to acknowledge him. I'm greatly indebted to him for helping me. There's a concept of Rube Goldberg machines, and there's a question whether life is a Rube Goldberg machine. Rube Goldberg machine is a contraption, it's an invention, a device or apparatus that performs a simple task in an indirect, convoluted, and complicated fashion. It's named after the American cartoonist and inventor Reuben Garrett Lucius Rube Goldberg. And here's a picture of a Rube Goldberg alarm clock. The bird here early bird bites on a worm, it triggers a pistol. The net result is this bowling ball falls on the man's nose, and in the process it also unplugs this water jar and just doses him with water. That's a picture. Now, in 1996, Michael Behe, in his book Darwin's Black Box, used the notion of Rube Goldberg machines to describe complex biochemical systems. He also used the word irreducible complexity, but personally, I prefer the idea of Rube Goldberg machine. So that was in 1996. Behe faced a lot of criticism, as many of you know. But despite that, in a 2010 biology textbook, Cell and Molecular Biology, 6th edition, figure 1.7 shows a Rube Goldberg machine, and it says here in the text, cellular activities are often analogous to this Rube Goldberg machine, in which one event automatically triggers the next event in a reaction sequence. And not to be outdone, the 2015 Nobel Prize winner had a 2008 paper, The Intelligent Clock and the Rube Goldberg Clock, and he uses the phrase Rube Goldberg-esque designs to describe the eukaryotic biological clock. So I've said rhetorically, is Paley's watch a molecular Rube Goldberg machine? I will highlight a particular Rube Goldberg machine that I like in biology. We have this DNA. So we have this chromosome here, and you can see as we zoom into the chromosome, it breaks down into this nucleosome, and in the nucleosome are this DNA. From the DNA, we can express, the DNA is used to express RNAs, and here's an RNA, the green strand. One of those RNAs is called the hot air link RNA. So just imagine this hot air link RNA transcript. That transcript originates from chromosome 12 here. It rides a shuttle bus, and the shuttle bus is called SUZ12. And that shuttle bus is propelled by the winds of Brownian motion. It goes from chromosome 12, it wanders over to chromosome 2, and in chromosome 2, it docks with this familiar thing, the polycomb repressive complex, PRC2. So we have this hot air link RNA, and it parks there. And it's responsible for telling this complex to set this lysine methylation mark on lysine 27. So it sets this bit. Again, you know, you have this huge machine that is just going to set one little bit there. So when we see all these memory marks here, what you realize is we're going to have a huge traffic of these machines constantly traversing the DNA. So it's this huge traffic jam that has to be coordinated. It's really amazing. So what is the Rube Goldberg aspect of this? Well, you saw some of it. I'll add a few more things. The link RNA is expressed strongly in cells below the waist but not above, and this causes skin at the sole of the feet to be different from skin on the eyelids. The hot air link RNA is also, not only does it write, in this case it acts to write memory marks on the histones. So it would be flipping the bits on here at lysine 27, but it can also erase. So on one end it can write, on the other it can erase. So that's what I call a God-made device, and that reminds me of this man-made device. Now, this picture of the polycomb repressive complex, there are many other complexes like this. They're composed of all these little machines too, these components, and they're quite complex. In some cases, in this picture here, the machine actually parks locally on the DNA, but that's not always the case. Let me show you something from the ENCODE 2015 conference. The molecular machines here will park on this section of DNA to service this section of DNA. So the black boxes here are the exons of a gene, of a particular gene called MMP13. They have not the most poetic names. They just kind of, it's like memorizing a phone book when you look at the list of names of the genes. But so we have this MMP13 gene here, but all the molecular machines park on the DNA here to be able to do their thing. So we were realizing that DNA just doesn't, it not only does it code for proteins, but it serves as a mechanical scaffold, and we really don't understand how it does this. Here's also another picture, Robert Tejan. He's the head of the Howard Hughes Institute, and it shows how molecular machines can park on one part of DNA and then interact with it, another part of DNA. So he indicates that they could be 1,000 kilobases away, and you can get these interactions. It turns out we can even have these between chromosomes. I do apologize for getting technical, but this is where some of the exciting stuff is. One thing about Rube Goldberg machines is it transcends the characterization of what constitutes good and bad design. It puts a philosophical twist on the bad design argument against intelligent design. And this was known in Darwin's time. The peacock's tail is a Rube Goldberg type machine, or Rube Goldberg extravagance. When Darwin saw it, it made him sick because it is so extravagant. It's why is this needed for selection? And that intuition was actually correct. It didn't stop Darwin from publishing a theory that I think is very flawed, but it did point out a problem. Natural selection should select against Rube Goldberg complexity, not for it. Darwin's theory equivocates the notion of selectively favored. Selectively favored in the present does not mean selectively favored in the past. That is, if you have insulin that's selectively favored now, it doesn't mean that insulin was selectively favored in the past when it didn't even exist. You can't select for what doesn't exist. In my opinion, Darwin's claim of natural selection is false advertising. It's contrary to experimental and observational evidence, such as reductive evolution and extinction of complex multicellular forms in the present. Some scholars think Darwin actually plagiarized the work of Edward Blyth. Blyth was the man for which the Blyth Institute is named, by the way. I think Blyth got it right. Natural selection is the mechanism of preserving species, not creating them. Now, briefly, here's a simplified explanation of Grauer's complaint, the genetic entropy. It's called Genetic Entropy by one author, Dr. Sanford. If ENCODE is right, the functional genome is around 3 billion letters of DNA. A big functional genome implies there are just more places where things can go wrong. And without getting into the details, this would imply about 100 bad mutations per individual per generation. To illustrate why this is a problem, I have this simplified haploid model of generation. So let's say you have a parent that had no mutations, and that parent has all these kids, and each of them has mutations. So even if we do survival of the fittest and take the most fit still has problems. And so now this kid, let's say this kid goes on to propagate, and he passes on his bad genes to his kids, and the kids also get some more mutations added to them. And you can see this process will just lead to genetic deterioration. So this was a simplified model. But it does highlight the problem with Darwin's and Spencer's idea of survival of the fittest. Survival of the fittest among siblings will not ensure that complexity will continue to increase. What they equivocated is they were suggesting survival of the fittest between ancestor and descendant. And you could see that there's a problem with that if there are bad mutations. Turns out my simplified model is pretty close to the truth. Hermann Muller, 1946 Nobel Prize in Medicine, he calculated that one bad mutation per generation per individual in the human line would be a genetic load that cannot be reversed. It would lead to inevitable genetic deterioration. This led one geneticist in considering this to say, why aren't we dead 100 times over? So Grauer's colleagues think we're past Mueller's limit by a factor of about 10. So even on Grauer's own terms, evolution is wrong. However, if ENCODE is right, we're past the limit by a factor of 100, and this is verified by numerous geneticists. One book that highlights this is Genetic Entropy by Dr. John Sanford, and that's basically the end of part 2. So I will take questions and comments. Thank you.
Okay, I'm unmuting everyone. Okay, ask questions.
Hi, this is Jim Johansson. I really appreciated your look at what you presented here. I have engineering background, and so studying the genome has been sort of a labor of love that I gradually have done. And so I probably would be viewing information as I'm getting into some of my research more from a bioinformatics point of view. But there's so many analogies that there's system design and the way things are laid out, and I know we're continuing to find more and more things that are there. And so first of all, I just want to say thank you for presenting this. I've heard of ENCODE, and there seems to be some mixed thoughts about it, but it's also interesting that it has a profit motivation, so it's not going to be that easy to kill if it actually can provide some therapeutic value and, you know, dealing with disease pathology and giving people relief that way. So I would enjoy kind of connecting with you further offline as I'm starting to look at some of my dissertation ideas, but I'm trying to play with the idea of is there some things about the human genome that to really fully understand it, you have to go beyond just a methodological naturalistic point of view, and I think you would soundly agree with that, but how can you start to measure that in a demonstrable fashion? That's one of the bents I'm trying to think about. So just a general comment, and if you have any thoughts about what I said, that would be great as well.
I actually think I have, even though I personally accept intelligent design and special creation, I actually differ from a lot of my peers in that I don't think supernaturalism fits in science. I think it's true, but I don't think it fits in science. That being said, there is a dimension, since you're doing bioinformatics, that, you know, obviously I think life is the product of a supernatural process. That's my personal view. If you're doing bioinformatics research, there's some dimension that is really powerful that evolutionary biology does not capture. It looks to me that the patterns of diversity and similarity in creatures, like we're much more similar to chimps, for example, than we are to trees. The ENCODE project and other genomics projects leverage that.
I seem to have lost Salvador. Can you guys still hear stuff?
Hello?
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 I can still hear him if you can hear me.
Yeah.
Can you hear me?
We
This
can
is Sal.
hear Salvador.
Yeah, I can hear Sal.
Okay, I'm going to mute everyone. We're getting feedback again.
They're able to actually identify functional regions based on patterns of similarity and diversity. And this is actually beginning to get leveraged by biotechnology companies. So if we assume that God created the patterns of diversity and similarity for the purpose of helping scientific discovery, that's something that really can't be explained by naturalism. It can be leveraged, however, even by methodological naturalists who have a profit motivation. All they have to do is just notice that there seems to be a language, a user manual just kind of incorporated into the genomes of various creatures. So therefore, there's interest in studying the the genome of the zebrafish to be able to understand us. And researcher after researcher just is, they're quietly amazed how informative it is to learn about ourselves by studying other creatures. This does, however, have a theological component because, or philosophical one, it's like, well, why should that pattern be there? Why does it seem that biology is optimized for scientific discovery, just like the planet Earth seems also optimized for scientific discovery?
All right, we are right up at 12. We have time for one more question, and then it's time for lunch. We can get going after that, though, if people don't want to go to lunch. Okay, it's unmuted again.
Hey, Sal. Yeah, Sal?
Yep,
Hello.
here. I'm here.
Yeah, this is Jim. I just wanted you to read my little note in there. If I can possibly get some of these slides from you, it'd be very informative. I'm doing a lot of stuff on analogy, and your PowerPoint presentation is full of analogy. And so I think it's incredibly useful, and it really brings it home to people who need something graphic in front of them. So I appreciate that. And,
Thank you.
Yeah, I will be doing a talk this afternoon that talks about analogy. So
I'm happy to provide the slides. I'm actually not the most tech-savvy person, so if there's some difficulty in me communicating it to you, and I think the other Jim was requesting them, is there a way that I could provide the slides some way to the conference participants so they could just access them? That might save, if we have some sort of internal website, I'm happy to just download it somewhere.
Well, one way, yeah, so we'll send them to John Bartlett and he'll mail them out to everyone.
thanks.
Yeah, that'll work. So like I said, I don't have the copyrights released. This is more of an internal conference, so I was happy using the material in that way. But I'm happy to share it with you. And by the way, a lot of those slides, some of them were just taken right out of the NIH presentations.
Wow.
I had another question. It sounds like you have some good contacts with NIH. What is their perception of some of the things that you're working on? Are they favorable to some of these premises that you have that are kind of steering away from an evolutionary point of view, or maybe that's not really a main context of what you talk about, but I'm just curious how those dialogues are going with NIH.
There are a few who are sympathetic to who are not naturalists, and I usually have to meet them kind of privately. When I'm at public conferences, I just have to pretend like I'm really no one in particular. I don't raise the issue. It's just way too sensitive, and it can cause a lot of problem in building relationships that are important to learning and being able to report on these things. So as much as I would like to get people to think outside the box and think outside of naturalism, it's kind of hard. But there is someone there who sort of helps. The director, Francis Collins, he called DNA the Language of God, and his book is actually on display at the NIH store. Even though he believes in universal common ancestry and a lot of evolutionary theory, he's not really a complete naturalist. He talks about Jesus a lot in his book. So me personally, I can't do it, but there's someone there at the NIH that if he wants to talk about Jesus at the NIH, no one's going to stop him, and he does.
Sal, I have a question.
Yes.
Yeah, this is Mario. One of the problems that I have with terminology, I guess, in general. When talking about science, you said something to the effect that supernaturalism should not be, in science or part of science or what have you. And I really think that it really boils down to the way we use terms. I always ask the question that if agency were to act in nature, is it natural? I mean, is it, or are we referring to artificiality versus what? And also, if to use an example, if we talk about meta laws, are meta laws, part of the natural world, or are they not? And it almost seems as though you always run into these difficulties once you start probing those types of questions in saying, natural versus supernatural. And of course, when we say natural, do we just, are we just referring to mechanisms or what have you? So any artificiality, if agency acts in the natural world, then that's not considered unnatural, or so do you kind of understand where I'm going with this?
I think I do, and because I debate, I really love debating evolutionary biologists. I've learned that I've not had an advantage when I start debating definitions. I have a lot more advantage when I just debate evidence. I really prefer not to say, well, do you characterize this as natural or not? I would prefer to just say life is exceptional. Whether you want to call it a miracle or not, it doesn't change the fact that it's a mathematically exceptional configuration. That's why when I pose, I'm going to show this diagram again. Boy, these are a lot of slides. When I pose the question like this, if I pose that to an evolutionary biologist, they feel very uncomfortable. I don't ask them whether this is the product of intelligence or not. I ask them a more basic question. I say, do you think this is an exceptional or a typical configuration? And I asked that about 500 coins on a table. And Mick Matsky, a nationally known evolutionary biologist, was very uncomfortable with the question. I was like, I got you. At that point I realized I got you in this debate, Right. Because the other side, the naturalists would prefer to argue definitions and follow every sort of red herring. They don't want to, I found that they don't want to deal with the evidence. And I just prefer not arguing terms. I just say, is this, and the most basic terms are exceptional or typical. I try not to even go into the realm of supernatural or natural, because that's defining the debate in their terms. I'd rather define it in these terms, and I've noticed it makes them really uncomfortable.
Yeah, that's a really good point.
And you could see that happening with the ENCODE debate. ENCODE is not raising the issue of natural or supernatural. They're just raising data, and it's making evolutionary biologists extremely uncomfortable. It's making them extremely uncomfortable. So much so they're starting to treat the ENCODE consortium like creationists. It's really kind of amusing. You can see all the vitriol coming out. I mean, you can see Dan Graur here. This is beautiful. This is the sort of thing you'd expect Dan Graur to be saying for a creationist. I just love that photo.